So I'd like to thank Theo for organising this seminar. I've enjoyed it a lot over the summer, and glad to be able to contribute today with my talk entitled Quantum Permutations Reborn. So first of all, I'll give a warning. So I told Theo I had a safe talk and a dangerous talk, and you're getting the dangerous talk. Now, I won't describe the various different ways that the talk is dangerous. I'll let you see for yourself. But I will say that I'm prepared to embarrass myself in the quest that I might provoke some thought and questions. Okay, so where we're starting with is, me personally, my research is in finite quantum groups. And I'm trying to properly learn about compact quantum groups, and I proposed to Klaus Kostler in UCC that maybe I could come in and do a seminar on compact quantum groups, because the best way to learn is to teach. And I'd kind of written down my motivation. I'd spoken about what I call the Gelfand philosophy. What is a quantum space? Well, it's the abstract spectrum of a unital C-star algebra. So a lot of us are familiar with this. Piotr would have spoken about it a few weeks ago. So that's the starting point. Second thing then is, for motivation, you want some examples. So you can talk about Wang's quantum permutation group, either two kind of ways of introducing it as a universal C-star algebra, or as an algebra of functions on a compact quantum group coacting on C to the n in the universal version of this, which is essentially in this kind of abstract picture. It's a universal quantum symmetry group of a finite set. So I had a little question about the reduced algebra of functions on a compact quantum group, just a technical question. And I emailed someone kind of explaining that I was trying to do this motivation. I had this little technical question. And they got back to me and they said, whatever about the technical question here is, if you're interested in kind of motivation, intuitions, here you have a quantum permutation. They said, oh, this somehow sends, whereas this certainly sends 2 to 4, this sends to a little bit to 4 and a little bit to 3, and they said, oh, this is kind of quantum. And I was looking at that and it's going, well, that's not really quantum. That's just probabilistic. That's just random. And I mean, you can do a distribution on S4 and you can produce something like this. Like there's no non-commutativity, there's no non-simultaneous observation. And it kind of got me on a dangerous train of thought. Just can a Gelfand philosophy talk of a quantum permutation? Because the answer really is no, because this isn't actually a set. So what I wanted to do, or where I ended up thinking about this, was kind of taking some proper inspiration from quantum mechanics. Now, this slide is obviously quite messy. I just want to say two things. So this UTR is under the rug. So I'm kind of making things quite easy for myself here. So for example, I'm just going to work with self-adjoint operators with a finite spectrum. And it's toy quantum mechanics. Now it's toy because I don't really care. Basically, I can interpret the maths however I want. I don't really care about the real world. In particular, in this, I'm going to have a sense of sequential measurements that might have all kind of problems in the real world, but I'm not going to worry about that. So I'm basically saying, okay, if you have a finite spectrum self-adjoint operator, it has an eigenbasis, orthonormal eigenbasis, nice spectral decomposition, and I'm going to think of this thing. So this is a state, and if I apply a projection here, I'm going to get the state, and I'm thinking this on conditioned on it will be if it was in this state, the observable would give me lambda I. And so in this sense, I kind of have that an observable is like a random variable. Two things happen. It gives me a value, say lambda I, and it projects down with this probability. This is essentially the Born rule, and you can get an expectation, something like this. And what I'm considering is once I have projected down onto this, I can measure with another random variable, finite spectrum self-adjoint operator G, and I can talk about the probability of starting with a state sigma, or psi, and measuring lambda I, and after that measuring lambda j. And formally, at least, we can certainly write down something like this. This product of probabilities is no issue here. And here we can kind of see the issue between or the difference between a classical and a quantum probability, where we can't really talk about the intersection of events. We can talk about this event after this event, or this event after this event, and they're not actually the same thing. So kind of looking at this, found in a book by Nick Weaver, Mathematical Quantization, the following quote: "The fundamental idea of mathematical quantization is that sets are replaced by Hilbert spaces, and the quantum version of a real value function on a set is a self-adjoint operator on a Hilbert space." And I said, well, yeah, why don't we do things like that, work with Gelfand and Neymark rather than Gelfand's theorem? So here we've kind of got this on the previous slide, and we may as well add in here. The issue is in quantum mathematics, these random variables are not simultaneously observable. They don't see the same set. So we're saying kind of when these self-adjoint operators looks at a Hilbert space, it sees a set. And for them to be simultaneously observable is for them to see the same set. Otherwise, it doesn't really make sense. And then, we can talk about the commuting after that. And of course, the after and before business will all coincide. So this is kind of saying, essentially kind of taking this a little bit literally. How about we take not an abstract spectrum, but a concrete Hilbert space to be a quantum space, and then we can talk about a quantum permutation simply being an element of the projective version of the Hilbert space. And we'll learn about the quantum permutation by making sequential measurements from the bounded operators. So this is a far more concrete way of looking at things than the Gelfand philosophy. It actually allows us to talk about a quantum permutation. The difficulty, of course, is we need concrete representations. So before we get into that, we also need to link the Hilbert spaces and stuff to actual permutations. So I want to talk about these UIJs that are going to be crucial to us. So this here is the algebra of complex functions on the symmetric group, and I can represent it as bounded operators on a Hilbert space here, the L2 of Sn. And basically the UIJ on a basis element essentially gives me the same thing if this sends j to I, otherwise it gives me 0. And these operators are projections, and under the rogue toy quantum mechanics, projections are essentially Bernoulli random variables, and so what I can do is their expectations are the same as a certain probability. So if I take, now this here would be a random permutation, be the language in the projective version of this. The expectation, which is not so important here, we're going to interpret this as an expectation, but of course the expectation should be the same as a probability because it's Bernoulli. And so this expectation of the random variable Uij, given with the state, the sigma state here, should be the same as the probability that it's equal to 1. And the way we interpret this here is as the probability that the random permutation sends j to I. Okay. Now, what we're saying is that if we have a fixed representation of the algebra functions on Wang's quantum permutation group on some Hilbert space, obviously this is highly non-trivial to actually do this, but if we could, we could define a Berkoff slice. So the Berkoff slice takes a quantum permutation, which is an element of this projective version of the Hilbert space, and sends it to the Berkoff polytope, fancy name for the set of doubly stochastic matrices. So because of the construction of this, with the rows and columns being partitions of unity, the rows and columns of this matrix here are going to be 1 as well. and so it's a doubly transitive matrix. I do want to I want to say I'm using the projective version because, as we'll see, we'll end up using things that aren't norm 1 anymore, and we're just going to normalize them out. And again, as we said, if these are expectations, we're going to interpret the entries of this matrix as the probability that this permutation, this quantum permutation, sends j to I. So now, of course, we want to condition. So assuming that the quantum permutation can send k to L, we can condition on it by multiplying by the projection. This will be non-zero if this is non-zero. We don't have to worry about it because we're in the projective version. We're going to normalize it anyway. So now what we'll do is we'll study, if you want to study the quantum permutation conditioned on this event, you can just multiply by this projection here. And so you end up with a doubly stochastic matrix. What is the probability that the quantum permutation sends j to I, given that it's just been observed sending k to L? And inductively, assuming as long as we stay away from zeros, we can study this thing here, which would be the probability that quantum permutation sends j to I, given that we've seen a number of things already. And assuming that we condition on non-null events, we can actually just multiply these things together, these probabilities together, to elements of the Berkoff slice, calculate these kind of things. Okay, so as I said, the issue was it's kind of a conceptual thing, and maybe that's all we have here, but we can still write down some nice examples. So quantum permutation groups, well, let's say things that are definitely quantum permutation groups, is if you have a compact matrix quantum group such that the fundamental representation is a magic unitary, then by the universal property of this is certainly a star homomorphism, and it's certainly going to intertwine in the right ways. You have a quantum subgroup. So as an example, you have the Katzpal-Eucken finite quantum group, which is the algebra of functions is represented on this 8-dimensional algebra, C-star algebra. And so take F1 to be this, F2 to be this, etc., I2, the identity here, and the following projection. We can show that the Katzpal-Eucken quantum group is a subgroup of S4+, which I know is in this Banica, Bichon, Natale paper, but here it is very explicitly and concretely. All the sums here are unity on the rows and columns, and we kind of have these little blocks. We'll see this is kind of the classical block, this is a bit of the classical, and the quantum action happens here. So this is an algebra of functions on C to the 6. Now, this is in the basis where this is kind of first thing, second, third, fourth, fifth, sixth. It turns out that E1 is the same as the identity permutation on 4 symbols. And what this means is the Berkoff slice of E1 is the permutation matrix of the identity. That means that it'll certainly send 1 to 1 or 2 to 2 or 3 to 3 and 4 to 4. And you can show, and we'll kind of see it later on, that it will be invariant. It'll be invariant under this algebra of functions. Similar story, E2 is classical, E3 is classical, and E4 is classical. So we have in this Hilbert space, we've got 4 classical permutations, and their span forms what we call some random permutations. Now, if we go into the 5th and 6th factor here, say this, it turns out that naively it appears that this can give you some permutations. So what we have here is, if you measure with this thing here, essentially measure where 3 goes, then where 4 goes, then where 1 goes, and then where 2 goes, your answers, if you record them, will be the same as one of these permutations, each with equal probability. And it's like, oh, you got these new permutations, and I suppose it's interesting that this is 8-dimensional, you've got these 8 permutations, but 3 of them are 1 to 1, 2 to 2, 3 to 3, and 4 to 4. And it's like, oh, you got these new permutations, and I suppose it's interesting that this is 8-dimensional, you've got these 8 permutations, but 3 of them are 1 to 1, 2 to 2, 3 to 3, and 4 to 4. And it's like, oh, you got these new permutations, if you actually measure it again, for example, sigma 1 here, you are not getting the same thing with probability 1. So just a little example of it, you can have this quantum permutation indeed can initially be seen sending 1 to 3, and then you see 3 is sent to 1, and then you see, now we've already observed 1 is sent to 3, and then suddenly we see 2 is sent to 3 afterwards. For random permutations, you don't see that. So this is a genuinely quantum permutation that we get a non-zero probability of this. It's also worth referencing, we just see a little uncertainty phenomena. Essentially, whenever we get a Berkoff slice looking something like this, once you know what's going on here or here, so if you know that 1 is sent to 4 and 2 is sent to 3, or 1 is sent to 3 and 2 is sent to 4, you're going to have complete uncertainty between 1 and 2 of where 3 and 4 go. And then once you observe, say 3 is sent to 1, you get this uncertainty here again. And you get, in fact, kind of get into this situation where if you keep measuring, you're just going to keep seeing going back and forth, and you'll never get a classical permutation like this. How about an infinite example? So probably the best way to do this is to work with this famous magic unitary that shows that for n greater than 4, Wang's quantum permutation group is infinite dimensional. So this is like the 1 minus p and p for just to make everything nice. This is the way I do it. And it's known that this is the same as the C-star algebra of the discrete group, the free product of Z2 with Z2. And if you want to explicitly show this, you can, well, this is the magic unitary that does this. So half E plus half delta U, and U and V are the generators of, respective generators of U and V in this. And so we get that this is a quantum permutation group. Now, if we want to talk about the quantum permutations, though, we need a Hilbert space. Now, what I've taken is there is a result Pedersen it's attributed to, and that the universal C-star algebra generated by two projections is isomorphic to this C-star algebra that functions from 0, 1 to 2 by 2 matrices that are diagonal 0 and 1, and these are bounded operators on the L2 functions from 0, 1 to C squared. And so you get a little inner product here. And so what I can do is I can take elements of this, and these are quantum permutations in here. And I will measure them using these things. Well, I'm going to be thinking of these things now. All right, let's go. So the explicit isomorphism here, or should I say here, is P is sent to this and Q is sent to this. So an example of a quantum permutation, something as an L2 function from 0, 1 to C squared, I get this. And so I can do the Berkoff slice of this, and live with something like this. And so the probability that this permutation, for example, sends 1 to 1 is 3/5. And then maybe I can condition on that event by multiplying by not P here. And so I'll get down to here. And so the probability that it sends 3 to 4 after seeing 1 is sent to 1 will be 2/3 by 3/5, which is 2/5. And we can continue, we can say condition on 1 is sent to 2, and condition on 3 is sent to 3, for example. And if we multiply together the respective entries of the Berkoff slices, we find that probability of 1 is sent to 1, 3 is sent to 4, and then 1 not sending 1 to 1 anymore, but sending it to 2, and subsequently not sending 3 to 4, but sending 3 to 3 is 3/50. Now we'll recall that for Katz-Palyukin, seat 6 we had classical permutations, and indeed the span of them is equal to this little Hilbert space. And so we kind of see this phenomena of classical permutations, the span of them is random permutations, and the span of them is, well, not the span of these, but they sit inside the quantum permutation somehow. Right, so we can see this even in an abstract way. So if you take a fixed and faithful representation of Wang's quantum permutation group, what we can do is form all these subspaces H sigma. So these are these are basically all the elements of the Hilbert space that their Berkoff slice is a classical permutation matrix. This is all this is. And for all of these, actually anything in here at all, restricted to one of these Hilbert spaces, it's a scalar. You can show elements of different ones are orthogonal. For each one in here, then you can just, this is basically just saying this. The next thing I don't think is necessarily that important, but I think you can shrink the representation to make all of these Hilbert spaces one-dimensional. I think you get exactly the same thing. But you can certainly choose a unit vector from each of these, and then you've got so these are like your classical permutations sitting inside your quantum permutations, and the span of them gives you your random permutations. And it's interesting to note here that this particular Hilbert space here, this one here, has no classical permutations at all, because if you take any pair from these, which are essentially the entries here, their ranges have trivial intersection of 0 intersection. But if you use a different Hilbert space, for example, a big universal GNS, and you do the GNS of the co-unit, then the cyclic vector of that GNS representation is a classical permutation. It's the identity permutation. That's kind of interesting. So if we haven't gone speculative enough, maybe we'll just take a little breather for a second before I go a bit mad. So if you wanted to kind of clean up the mathematics, when you're playing poker with a quantum deck of cards, you can only look at one card at a time. So you can lift up the first one, then lift up the second one. On the first site, you might find 3 aces of hearts and 2 aces of spades. So you find an ace of hearts. Now, of course, you won't find an ace of hearts in the next card, but you might find an ace of spades. And then the third card, you can find the ace of hearts again. And then the fourth card, an ace of spades, and the fifth card, an ace of hearts. And you bet as hard as you want. You think you're going to win. And of course, when you go to show your hand, you show the first card. It does not necessarily have to be an ace of hearts anymore. It could be a 2 of clubs. And yeah. So what else have we got here? So this kind of way of thinking kind of explains why there's no quantum S3. Basically, you can measure. So when you know where the first goes, essentially the 2 and 3 are then entangled. As soon as you measure 2, you know 3, and as soon as you measure 3, you know 2. And that's kind of an explainer of why there's no quantum S3, but that doesn't happen for S4. Quantum permutations in the lab, you can probably formulate thought experiments for the lab and kind of ask experimenters, have anything like this been done? Like similar to what we saw with the GNS of the co-unit, you can think about the co-unit, the antipode, and the quantum group law kind of in terms of things we know already. And for me, it seems to me that you can actually, the tensor product here in the Hilbert space gives a quantum group law. I don't see anything, an issue here. You can invariant subspaces, sub-objects, be it simply a one-dimensional subspace where that represents classical permutation, or a bit more fully, maybe actually a quantum subgroup. I don't know how much that can be pushed though. Dual finite groups, I'd like to do something. I know I've done a little bit there, but I think the dual of S3 is in this thing. And now I'm going to construct a magic unitary and see what kind of behaviors we get there. What else? The Hopf images. So this is the thing we saw ages. It isn't a quantum permutation. It's a measuring device for measuring quantum permutations. It's not a particularly good one. It can't capture, for example, the identity, but if you kind of, it can be augmented minimally. And this is the Hopf image. So this is kind of what we're, so in that sense, this is a way of thinking of Hopf images. Next thing, getting more speculative, unobserved random walks on Sn plus. I have a feeling that they behave classically. What I mean by unobserved is you just let the distributions multiply away. Don't make any measurements, and I think they're going to behave exactly classically. Some evidence for this is that random transmission random walk on quantum Sn plus converges at the same rate as the classical version, half n log n. That's Amori, Verlan, postgrad Lucas, and Siming Wang. Something's going to be relevant to something that I look at in a few minutes is there's a kind of a dichotomy of fast and slow convergence of products of projections, powers of that, onto the intersection of their ranges. Yeah, we'll see this. And then beyond symmetry, quantum symmetry. So, for example, what about, can we talk like this about quantum symmetry groups of the sphere, etc. So, if I haven't insulted you enough with this talk, I'm going to go a bit beyond here. Okay. So, one of the things I thought about, I was actually looking for a representation of Wang's quantum permutation groups, and I thought maybe somehow I'd be able to do it with random walks. Now, I failed completely. This is where all this is coming from. But one thing that I didn't have in my head would be kind of an intersection of random walks with this kind of thing. And, well, we'll see. Okay, so if we take a quantum permutation, and if you make some sequential measurements. Now, what I mean by random is maybe there's a finite number of these. It's an infinite. You're going to keep measuring. But maybe we don't specify in what order we do it or whatever. But you can do it random. I mean, that shouldn't be an issue. So these will produce a random sequence of quantum permutations. Okay? And essentially what I'm thinking about here is that you are learning more about the quantum permutation. Of course, you're changing it, but you're learning more about, you're kind of narrowing down what you know about it. Kind of making these measurements, you'll find more and more about it. And essentially what you're kind of hoping is you get to a stage where maybe there's some kind of limiting behavior. Okay? What I'd be interested in is, could it be that eventually these things start ending up as classical permutations? So we could kind of talk about this probability. Again, this is very speculative. We could find out what's the probability that this is classical. Okay? And the question would be, how does this thing grow here? It should grow from 0 to 1, because if you're in this, if you land in one of these, if this is a classical permutation, it's invariant, you're just going to stay in there. So how does this grow? And note, we've seen already that it'll always be 0 on this. So some little examples here. So if we just talk about even on S3, very simple example, and you measure it, does it send 1 to 1, does it send 2 to 2, does it send 3 to 3, does it send 1 to 2? And this is essentially a superposition of all the permutations in there. So after one measurement, it isn't enough. After 2, there's a 50% chance that you now have a classical thing on your hand. After 3, there's a 2/3 chance you've classical permutation, and after 4 measurements, after measuring this, that's enough to specify to end up with a classical permutation. Now, of course, it can go in many different ways, so be it. We can also do this with Katz-Pal-Yukin, where we're going to measure with this order, again, a similar kind of quantum permutation. And it's kind of the same, but actually once you get up to 3, you can't do any better. This uncertainty thing kicks in, and you can never pin it down to a classical permutation. Could we possibly restrict to quantum permutations and measurements that eventually go classical? Might be somehow interesting, and this is where I'm really reaching in China. Could it grow for some state So this is in the set of states on the algebra of functions, that it'd be, you look at that somehow this would happen. The reason I'm saying this is we have tools to analyze this. We have tools to analyze this. Now, I haven't done it so Amori, for example, and has done a lot of work on this, analyzing this, that basically what would happen is somehow every time you make a measurement, there's a convolution happening somewhere. And that this probability might grow like this, that 1 minus this. And then you see what's interesting is we have this cutoff phenomena. So a family of random walks given by a suitable natural family of states, and that it might turn, and it turns on the cutoff phenomena. Essentially, this number is very far. It's very far from random. So this distance is very large up to a certain point, and then there's an abrupt transition where it becomes very small. And with the 1 minus, it would look something like this. So essentially the idea would be that up to here, you're making all your measurements, but you have not identified a classical object. And then very, very abruptly, the probability that you identify a classical object gets very, very large. And I think this would be a really, really cool example. Because what it would be, with the n going large, as the system goes macro, as n goes really, really large, the sequential measurements suddenly reveal a classical object, which I think is really, really cool. So for my final slide, thank you for listening, or else you need me to say, I'm sorry.